the doctoral candidate, Cristina Isabel González Osorio. Cristina, you have 40 minutes to present your doctoral dissertation, after which we will follow up with an open-ended interview with the jury.
Great, so hello everyone, my name is Cristina González, and today I will be presenting for the next 40 minutes the PhD thesis defense. So this work is advised by Professor Pablo Velázquez, and the examination committee includes Dr. Jordi Pontuset, Dr. Juan Carlos León, and Dr. Luis Felipe Girat. So as an overview of what we will talking about today, so the first thing that I will do is give you the motivation and the introduction of my work. Next, I plan to explain all the approaches that we took to approximate artificial intelligence model towards open-ended visual recognition. And finally, I will conclude and give you and share some thoughts on future perspectives. So, particularly for the introduction, I will introduce how the visual recognition problem has been studied, and also I will mention some of the challenges that we have in the open set scenario. So traditionally, visual recognition has been studied within a closed set scenario, and so as in supervised approaches, we have so as in most supervised approaches, we split the data into a train set and a test set. But more important, we train and evaluate our models in a fit set of semantic categories. Since like this approach has led to significant advancements in visual recognition, however, this has some limitations in terms of how we represent the data. So that brings us to the concept of representation learning. So in the closed set scenario, we have a default representation from images or objects in our case. And we can train a neural network to produce a semantic representation. And we hope that this representation is discriminative enough to be able to distinguish between the objects that we have, right? In contrast, in the open set visual recognition scenario, we also split our data, but we train on a fit set of semantic categories, and we may encounter some novel categories during testing. So in this case, we have this new object that is the stacking tower. And so the model must be able to recognize known categories while also being able to handling novel ones. So this is more like a review of how the community has studied visual recognition. So the course's problems that we have is image classification and image captioning. So in this case, we have an image. What we want to produce is a textual description or assigning a semantic label to it. However, if we want AI models to be able to achieve or perform more complex applications in real-world scenarios, we need our models to be able to spatially localize within the image the semantics. So from this point, we can split our task into two subtasks. So the first one is spatial localization of visual entities within the image. And the second one is assigning a semantic label to this spatial localization that we're doing. So particularly for object detection, we are assigning a semantic category to bounding boxes or windows within the image. This task is usually focused on things categories, like the ball and the bench in our example. And these categories are usually countable objects. However, we can go one step further in the localization task and delimit the boundaries of the objects that we have, segmenting it. And we also assign the semantic category. From the output of this task in instance segmentation, we can notice that we are ignoring a lot of information semantic information fitted within the image. So that's why semantic segmentation proposed to assign a semantic label to each one of the pixels in the image. So including the amorphous regions that we have in the background, like the trees, the grass, and the bushes. In addition to that, we also consider things categories like the ball on the bench. Finally, phonetic segmentation is the more general version of this problem. So what we want to do here is using the prior to task. So we are using instant segmentation for things categories, and we are using semantic segmentation for stuff categories. So more recently, there have been some work that has focused on spatial localization mainly to be able to like enable this model to generalize to other categories. So these models focus on spatial localization while ignoring the semantics of the segments that we are recognizing. Yeah, that gives us the possibility to also be able to recognize and like delimit spatially the node categories that we have, and this task is known as entry segmentation. However, the end goal task for our community, at least in visual recognition, is the open-ended recognition. So in this case, we want to generalize in both dimensions. So in the spatial localization dimension by segmenting visual entities, and in the semantic dimension by describing these objects with open-ended descriptions. My thesis focused on bridging the gap between these two tasks by keeping like the sadness that we have in entry segmentation with semantics using natural language. So natural language, in addition to give us the possibility to express semantics as humans, it also enables us to generalize in known categories and also produce outputs that are more flexible and interpretable by for human computer interactions. So that's how we propose the following research question to be solved in this thesis. So how can natural language be leveraged in case to enhance open-ended visual recognition task, enabling models to achieve precise spatial grounding, generalization to new categories, and robust semantic evaluation. So rather than tackling the problem of open-ended visual recognition all at once, my thesis follows a progressive approach. So the first thing that we do was focusing on task formulation. So in this case, we propose a task formulation that enables us to study the problem of learning a joint space between vision and language, while preserving the spatial localization and the semantic detail in the task. Then we took one step forward to try to build a model to learn this joint representation space. We extended to the open vocabulary recognition task. And finally, we arrived to the goal task open-ended recognition and propose some evaluation metrics to include some different semantic levels on it. So let's start by the task formulation goal. So if we go back and recap the limitations that we have in the closed set representation space that we were learning. So if we try to recognize a novel object, then these models will probably misclassify as one of the known categories that we have. There have been also other approaches that try to design representation space that is more flexible. So in this case, we can recognize the known categories, but also like recognizing some novel characteristic of unknown categories. So in this case, if we try to categorize this novel object, then we will at least know that this is not one of the known categories that we have in the training set. However, we don't have like an intuition of what is the semantic meaning of this object. So that's why we propose using natural language, and in this case, we can build a representation space that is structured by the implicit semantic of natural language. And in that way, we can recognize the known categories that we have during training, and when we try to recognize the novel object, at least, even if we don't know the exact semantic category, we at least have an intuition that this thing is a toy from the representation space. And this is similar to how we humans describe unfamiliar concepts from when we don't know a new object by describing it with the semantic knowledge that we have in the past. So that's why we propose the specific research questions of which task formulation enables to study the alignment of natural language and visual data while ensuring both fine-grained spatial localization and semantic reasoning. So this paper is the ones that solved this question. It is called Narrative Grounding. This was a collaboration done with Google Research Zurich. It was presented at ICCB 2021 as an oral presentation. So among the many problems of the intersection of vision and language, we focus on those that produce a visual output because our community has developed a strong frameworks for their evaluation. So in this case, we will focus on the problem of visual grounding of natural language. The first attempt to propose this task was referred, and in this case, we want to segment the object that we have in the image according to a short description, like the ones shown in this sample. With time, subsequent works start to focus on more complex problems by doing visual grounding at the word level and linking bonding boxes with noun phrases that we have in the caption, as in the figure 30 they enter this data set. More recently, localized narrative introduced longer textual descriptions that are temporarily aligned with user mouse traces, as shown in the image. So previous frameworks contain sufficiently dense annotations over language. However, over the visual dimension, there is still very sparse. So that's why we propose to transfer localized narrative annotations to Google Analytics segments, and we propose panoptic narrative grounding. So here the task is given an input image and a long textual description. We want to densely ground in the image of the noun phrases that we have in the caption, as shown in the animation. So how we do this? So we propose a benchmark, including ground truth annotations. So in this case, we propose to transfer the localized narrative annotations to segments. And so basically we assign a region, a ground truth region, corresponding to the mouse trace that we have in the annotation from localized narrative. We try to check that these matches are meaningful. So we compare the noun phrase that we have and the ground truth label of the semantic category to ensure that these two elements semantically agree. So for example, in that last example, we were assigning a region cat to the noun phrase cat, so it was an exact match. However, we also considered more complex semantic correspondences, like synonyms, hierarchical relationships, and meronyms. So, for example, in this word cloud, we can see that we are assigning a region with a labeled bird to any of these words like big and feathers. In this slide, we can see some examples of our transfer annotations. So we are temporarily and spatially aligning noun phrases, user mouse traces, and phonetic segments. Okay, so now we also propose an evaluation metric. So let's consider an example. So we have this image and this caption with highlighted the noun phrases. So Okay, so we have also the ground truth segments associated to each of the noun phrases, and we can assume that these are the predictions that algorithm is producing as an output. We can also compute the intersection over union between the ground truth and the prediction. Setting a threshold, we can determine which are the true positive and false negative of our method, and then compute recall. That will give us a point in the intersection over union and recall plane. And then if we vary this threshold, we can obtain a curve. And so the area under that curve will be our final metric that we call average recall. Okay, so to conclude, these are so we propose fanatic narrative grounding, which is a bus that aims at creating fanatic segmentation that grounds densely each noun phrase in a language description of an image. And in addition to that, we introduce a new benchmark based on localized narrative and MS COCO for the study of this task. And we introduce a stricter metric measuring both recognition accuracy and segmentation. Now let's go to the step in which we try to build this joint representation space using a method. So in this case, we propose Piglet. It's a level grounding of language expression with transformers. This work is also a collaboration with Google Research, and it was published at PAMI in 2023. Okay, so the research question that we want to solve is how can we develop a method to build a joint representation space that effectively integrates visual and language information? And so this is an overview of our method, which I will now explain in detail. So the first thing that we have is the long text descriptions, and we would tokenize it and pass it to a language transformer to learn some embedding representation for this modality. So for the image, we will do the same. We'll pass it through segmentation methods. In this case, it's mass transformer, and that will give us some embeddings for each of the mass, and also these embeddings are associated to mass segmentations. Then we will concatenate both branches of information and process it with a corresponding transformer. And from that, we can compute a similarity metric between both modalities. So, which in this case corresponds to the noun phrases and the visual entities that we have recognized by the segmentation model. We compute the cosine similarity between these two things, and as in for inference, we are selecting the visual region that is more relevant for each of the noun phrases that we have in the caption. And this is an actual output of our method. So regarding the quantitative results, we are comparing also with the method that we propose when we propose the task. So this is our baseline. We can see that we bigly outperform the baseline significantly, achieving an average recall performance of 65.9. Since we are taking as input segments, we can compute an oracle. So in this case, we are selecting the segments like the prediction with the highest overlap to the granted segment. So the gap between our methods and the oracle will correspond to the matching errors of our model, and the remaining area will correspond to the segmentation errors, as shown here. We also did a comparison with the state-of-the-art models that were developed for the previous version of the problem, which was referring expression segmentation. So since this task is focused only on teams categories, we disaggregate the performance just for that to make the comparison fair. And so NCN is the model that was listed there in the previous task. We can see that our baseline and Piglet both outperform it significantly. Okay, so we also can disaggregate our performance between things and stuff categories. So even if for things categories we have a 2-point absolute difference with the stuff, and this is higher, we can see that the gap with our Oracle performance is higher for things categories. We hypothesize that it can be because the intervariability in things categories is higher, and the model also have to be able to discriminate between multiple instances of the same semantic category within an image. And does not happen for stuff categories because we only have one instance per category. Finally, we disaggregate the performance between singulars and plural nouns. So in this case, we can see that the gap for plural nouns is higher. So the model is failing to retrieve all the exact amount of instances that the plural nouns are referring to. These are some qualitative results that demonstrate the accuracy of our method. Additionally, we can see that there are some segmentation errors that one that we highlight here. So, this is more like a diagnostic example because here we can illustrate all the failure modes of our method. So the first thing that I would like to point out is that the model fails to this ambiguity between the person who is standing and the person who is playing with the ball. And the second thing is that our model is restricted by the recall and the accuracy in the segmentation of the segmentation model. So here we can see that we are missing one part of the car, and we were also missing the segmentation of the ball. And finally, with respect to the plural nouns, we can see that our model fails to disambiguate also between all the people in the image and the people just standing in front of the building in the background. Yeah. So to conclude, we introduced Piglet. This is a multimodal architecture for pixel level visual grounding that matches segmentation regions to a specific node, for instance, in the caption. And our model achieved state-of-the-art performance for open narrative grounding, for phonetic narrative grounding. So now we can extend this to the open vocabulary visual recognition task. So let's take a moment to make a recap of the joint visual space that we have built so far. So in this case, we are using the language implicit semantic information to build this representation space. However, in our method, it is still restricted to known categories in the MS COCO dataset, which is the benchmark that we use. So it will still fail to generalize to new unseen categories. So in parallel, our researchers propose a model that learn this joint representation state within vision and language that is called CLIP, for contrasting language image pre-training. So CLIP was trained using a large scale data set of image and text pairs. So basically we train a test encoder to produce some test embeddings, and we also do the same for the visual information with the images. And then we can map these test embeddings to the representation space. And we can do the same with the visual information for the images, right? And so we can compute the cosine similarity between these two embeddings and perform contrasted learning, which aims to minimize the distance when these two modalities match, and maximize it when they don't, like here, right? And we call this contrasted learning. So this may seem very similar to what we had before, but there are two key differences. So the first one is the level of representation. So we are learning representations between visual regions and language. So then we are keeping the spatial localization of the semantics. Our clip is learning representations for image and language. So so these models were suited for tasks like image classification and image retrieval, but fails to have this spatial information. And the other thing is the scale of training data. So we train our model on BMS COCO dataset, which is highly curated but small in size. And the clip model was trained on 400 million image test scores, which is like really broad, extracted from the internet. So the semantic information that this model has is massive. So now what we should do at this point of research was to like leverage clip to make it to adapt it for a region-based task. So we can do that by replacing the captions with the categories that we can have in visual recognition to learn this representation space. And we can do the same by replacing the images with regions in the objects. And we can still train this model using contrasted learning. So the research question for this task is, how can we leverage clip image level representation space to enable models to generalize region fits categories for open vocabulary visual recognition? So this paper is called Region Task Alignment for Open Vocabulary Region Recognition. This was a work done while an internship at Adobe Research. So we have two objectives for our approach. So the first one was decoupling recognition from segmentation. So as I mentioned before, there were some models that can produce some high quality segments, but these one are class agnostic, like SAM and intersect. So we decide that we can do the same for recognition. So we can ignore the part of segmentation. So we in our task, we are defining that we have as input the image, the segments that can be granted segments or the ones that are produced by these segmentation models, and a vocabulary of categories that of the objects that we want to recognize, and we want to build a mass aware labeling model to basically classify the segments that we have. So in the datasets that we have available, we can see a trade-off between the semantic range and the spatial localization, particularly if we consider image level labels, which have like a broad semantic range, but the spatial localization is very raw because we only have image level catches. In contrast, we can have for the visual recognition datasets, the segmentation datasets, we have really like a strong signal for visual spatial localization. However, the concepts are really restricted. The concepts that we have in these datasets are restricted. So we want more to strike a good balance between both things. So we want to have a strong spatial visual supervision with a more semantically constrained settings. We want to also exploit mass guided with supervision with broad semantic concepts from image level data. So this is an overview of our methods. We have two learning objectives that I will explain now in detail. So for the segmentation and detection datasets, we have these inputs. So we have the image, the categories, labels, and the segments or bounding boxes or points. In this case, we are using clip, text and image and text encoder function. So we have we can extract a multi-scale visual representation from the image, and then we can train mass encoder or visual from encoders to produce some representations here for mask for regions in the image. And we also have this the frozen text encoder from clip to produce some representations for each of the categories that we have. then we can compare these two representation spaces as we did, and we can just compute cross-centrifugal here to make contrastive learning. And for inference, we can select the category label with the highest QS with the highest score for each of the segments. Now, if we only have an image and a caption, we want to take advantage of this. We can use a mask generator to produce these high quality segmentation masks. And then, as we did before, learn these mask representations. We can have this global representation for the caption using flip test encoder, and then we can learn this region test alignment function that I will explain in detail. So we have a set of captions that we can encode using our test encoder, and then we have an image, and we can represent this image in the visual entities that it has, right? And so we can compute the cosine similarity between all the captions that we have in a batch and all the segments that we have for that image. And that can give us some weights to, according to the similarity between the regions representation and the captions. We can use those weights to produce a global representation for that image, like doing a linear combination of the embeddings. So then when we have a global representation for each of the images, we can continue doing contrastive learning as we used to do in here. Right. So now for the experimental setup, these are the models that from the state-of-the-art and which we are comparing to them. These are the data sets in which these models are trained. This is our method, which is called region test aligner. These are the benchmarks. So we have Edison, Mapre, Vistas, and Trisite. As you can see here, we are evaluating on novel data sets. So we can include like evaluate the generalization capacity of the model. So we have two versions of our model, the one that is saying only on COCO and image level and image test per data, and the one that is saying on multiple data sets, just to see how these generalize or escape with data. We are evaluating metrics related to recognition only because we are taking as input the ground truth segments for each image. So we have precision, recall, and recognition quality from the connective quality metric. And we can see that our model outperforms previous state-of-the-art in all the data sets. So these are some qualitative results to show how our model is doing better. So these are the images, this is the ground truth segments, and this is our model compared to previous state-of-the-art methods. We can see that our model is able to recognize that this ambiguity between castle and temple, and also the model is able to recognize the trees, like trees, and not confuse it to other related semantic concepts like branch or scope. These are some qualitative examples to evaluate how our model was doing with image in the wild and what we can do if we change the vocabulary that we're using. So here we can see that our model is able to discriminate between a buck and a schnauzer, which are different dog breeds. Also, our model is capable of discriminating between a stuffed rabbit and a real rabbit. So to summarize, we introduced region test aligner, which is a method designed to benefit from multi-source spatially aligned semantic data and large-scale image tests per data. We also formulate another similarity function for image tests per data by considering the alignment between ground truth captions and mass predictions from robust open-ended segmentation models. And RTIO performs existing methods across 3 benchmarks for open vocabulary phonetic segmentation. And so finally, we end to our end task, open-ended recognition evaluation. So here we're going to be focused on evaluation. So for this task, we not only need we cannot use the representation space that we were using before, but we need a model that is capable of generating tests. So we are considering now multimodal large language models, which should be pretty familiar to you, since they are very popular right now. So we have ChatGPT, Gemini, Copilot. And these are our view of what these models do. So we have as input an image and also a textual question. We can use a visual encoder to encode the image into visual tokens. We can do the same with textual information using a text tokenizer and then an embedding layer. We concatenate both branches of information and pass it through a multimodal large language model. So this is an autoregressive transformer that can generate text that is conditioning on the input that we are passing through the model. So as a recap, this is the class formulation for this last chapter. So we have an image, and the proposed output is like the aim of this task is to produce spatial localization by segmenting regions, while also generating some meaningful textual descriptions for each of the corresponding regions that we have recognized. So for the evaluation framework, we have to consider that we are now using, we have a generative output. So how do we evaluate generative models? So historically, evaluation models have been evaluated using user studies, but this can be pretty costly and also subjective. Other approaches like the FID and the insertion score propose to use pre-trained models. However, these models fail to like generalize or adapt to novel data distributions. So these limitations are probably fixed for image generation. However, when we are generating this, we can also use the implicit semantic structure that we have in language. So that's why we propose the following research question. So how can we evaluate open-ended visual recognition models considering different levels of semantic alignment? So this work is titled Open-ended Visual Recognition Evaluation. This work was done also in collaboration with Google Research. So let's consider an example. So if we have an image and the segment associated to this image, we can also have the ground truth category of them. Let's assume that this is the output of a multimodal LLM. So the first thing that we are going to do is to extract the noun phrase or the subject of these descriptions, and then considering different semantic levels, we can determine if this noun phrase is a false positive or a true positive according to the ground truth label that we have. So for example, in this case, for the submatches, we didn't have an exact match for any of the segments, but for synonyms, we can say that elbow share is a synonym of archer. So now this is considered a true positive. It is worth notice that our semantic labels are cumulative. So this will continue to be true positive for the remaining semantic labels that we have. We are also considering hyperlink. So for example, dance home is a hyperlink of dog. So now this is a true positive. And we continue doing the same for the remaining semantic labels that we consider, which are metonyms and also semantically related concepts. So now, having this definition of true positive and false positive and false negative, we can compute any visual recognition metric, like the phonetic query in this case, for each of the, like putting a threshold on each of the semantic labels that we have defined. So that would give us a curve, and then our final metric will be the area under that curve. And so now, to compare for our experimental setup, we want to evaluate the performance of state-of-the-art open vocabulary visual recognition models. We want to like adapt them to the generative task. So the first thing that we do was to pass a comprehensive list of nouns as the vocabulary for these state-of-the-art methods, for them to produce a classification. And these are the methods that we are considering. The other thing that we did was to propose a baseline using a multimodal LLM out of the box, and passing the image and ask this model to produce to provide a list of the vocabulary or of the semantic vocabulary that we have in the image, and then use this output as the input for the best open vocabulary model that we have in the CDR. Finally, we compare it to Osprey, which is a generation model that is trained for generating, which is a multimodal LLM that is trained for generating descriptions for mask associated to an image. So in this case, in this curve, we can see these are the open vocabulary visual recognition models adapted for this task. And these numbers are here at the area under the curve. We can see that this is our baseline performance, which is better than previous state-of-the-art. And we can see that we are better for SAT and synonym matches. And finally, we have Osprey, which is the generative model. And this one is better than all previous evaluated methods. And that was for bioanalytic segmentation. This is for semantic segmentation. So in this case, we can see that our baseline is better than the generative model. So this is suggesting that our baseline is better for staff categories, as we can see in the next slide. Osprey is way better than previous state-of-the-art in for things categories, since we are here evaluating instance segmentation. So to conclude, we introduce a novel evaluation framework redefining recognition metrics, considering semantic relationships. Our metric enables deeper insights into model performance across varying levels of semantic alignment. And our evaluation, hopefully our evaluation framework will push the envelope further in the development of open-ended visual recognition methods. So to conclude, we leverage natural language to approach open-ended visual recognition. And so the first, in four stages, so the first stage was task formulation. And we propose a experimental setup and a novel formulation for natural language visual grounding, preserving both spatial localization and semantic detail. We developed a multimodal model architecture to align segmentation regions with phrases in caption. We enable recognition of unseen categories by decoupling spatial localization from semantic labeling and leveraging multi-source supervision. And finally, we introduce an evaluation framework redefining metrics by incorporating diverse semantic relationships. So future perspectives. We have the intuition that maybe this gender representation space that we build for the open vocabulary segmentation task may be useful also for the generation task. So I think this is a research part that is worth exploring. We need also interactivity and feedback. So this will enable the recognition model to be able to disambiguate the recognition that is doing according to what a user can input. We can enrich the recognition model using multimodal information coming from audio, from depth, or even for video. And I think that that will make recognition models more powerful. Finally, I think there is a huge gap in cultural adaptability since we have some both visual appearance of objects can vary across different places in the world, and also like the descriptions that we are using for these objects can vary across different cultural settings. And so this is the list of publications that I have done during this PhD.